Welcome to the next lecture in Chapter 6. Here we're covering 6.5 and we're going to figure out how to calculate the length of curves. So when we're talking about the length of curves, here are a couple examples. Imagine the space station which orbits the Earth in an elliptical path. How far does it travel in one orbit? Another type problem is a baseball slugger launches a home run into the upper deck and the sportscaster claims it landed 480 feet from home plate. But how far did the ball actually travel along its flight path? Here you can see an example of a trajectory. These questions deal with the length of trajectories, or more generally with arc length. As you will see, their answers can be found by integration. There are two common ways to formulate problems about arc length. First, the curve can be given explicitly in the form of y equals f of x or some functional equation, or it can be defined parametrically. In this section, we're going to deal with the first case. Parametric curves and the associated arc length problems are going to be discussed later in section 12.1. So let's look a little closer at an arc length. Suppose a curve is given by y equals f of x, as you can see in the image here to the right, where f is a function with a continuous first derivative on the interval ab. The goal is to determine how far you would travel if you walked along the curve from a f of a to b f of b in the image to the right. The distance is the arc length, which we will denote by the letter L. If we continue in the pattern that we've done with other shapes and figures, etc., and to find other units of measure, if we divide the interval, the closed interval AB, into n subintervals of length delta x, which equals b minus a over n, where x sub k is the right endpoint of the kth subinterval for k equals 1 all the way up to n. By joining the corresponding points on the curve by line segments, we obtain a polygonal line with n line segments. If n is large and delta x is small, the length of the polygonal line is a good approximation to the length of the actual curve. The strategy, as we've used before, is to find the length of the polygonal line and then let n increase while delta x goes to 0 to get the exact length of the curve using a limit. So what we have to do is figure out a formula for that polygonal line for each segment and then apply the limit. So let's look at a subinterval much more closely and see if we can figure out a formula for that line segment. So let's consider the kth subinterval highlighted in the image to the right. And we can see that delta y sub k is equal to f of x sub k minus f of x k sub 1, k minus 1. That's just the y2 minus y1, right? And since we can see that the kth line segment is the hypotenuse of a right triangle, we can see here in this circle diagram, we know that x squared plus y squared equals the hypotenuse squared. So we can find that hypotenuse length by taking the square root of delta x squared plus delta y sub k squared. If we sum all these lengths, we get the overall length of the arc is equal to the summation of all of those lengths. Now normally, once we get to this point, we simply apply the limit as n goes to infinity, and then we can integrate. But unfortunately, we have another term in here. Instead of everything being defined in terms of x, we have a delta y sub k here. So we need to simplify this equation first. From the prior image, we saw that the slope of the line segment, delta y, is delta y over delta x. And we know by the mean value theorem that we covered in Calculus 1 that if a function is continuous over a closed interval, then there has to be some value in there where the derivative, the instantaneous rate of change, is exactly equal to the average rate of change, or the slope, over that interval. And so if we use that someplace along that segment there's a derivative that actually is equal to the slope, or delta y over delta x, we can do some algebraic manipulation, as you can see to the right. First, factoring out a delta x squared. Then notice here we get the slope squared, 1 plus the slope squared here, and we can substitute in, we can substitute in f prime for that slope. Since we have the square root of delta x squared, we can take the square root of that, and we get delta x outside of the radical. And now we have it in a form that is all defined in terms of x and f of x, and its derivative. And so we can now apply the limit as n goes to infinity and define the arc length in terms of an integral. The length of an arc is equal to the integral over the closed interval AB of the square root of 1 plus the derivative of f at x sub k squared dx. So that brings us to the definition of arc length for y equals f of x. Let f have a continuous first derivative on the interval AB. Then the length of the curve from a f of a to b f of b is L equals the integral from a to b of the square root of 1 plus the derivative of f of x squared dx. So let's look at our first example. Find the length of the curve f of x equals x to the 3/2 between x equals 0 and x equals 4. By looking at the image, we can see that the curve is continuous between 0 and 4, and so we can apply the definition of an arc length here. So we need to find the derivative of f of x, plug it into this formula with the limits between 0 and 4. So go ahead and try this problem. It's really a straightforward integral. It's just what I call a plug-and-play problem. You've got a formula, you need to find the derivative, and then plug it into the integral, and then use the techniques of integration that you learned in Calculus 1. So go ahead and hit pause and see if you can solve this problem. So here we can see the integral, and I'm not going to walk through a lot of this. This is directly out of your textbook. You can go look at this. I'm not going to spend a lot of time here. It's just simplifying it and then doing a substitution. Substituting u equals the radicand, what's inside the radical here, and then making sure that we offset with the reciprocal of this multiplier for the derivative. Since we don't have 9/4 inside, we offset it by multiplying the entire integral by its reciprocal. And again, these are techniques you should have learned and remember from Calculus 1. You might want to go back and look at your integration techniques, especially substitution and implicit, etc. Okay. And the total here, when you do this out, you should have got 9.1 units. So let's look at our next example for arc length calculation. Find the length of the curve f of x equals x cubed plus 1 over 12x on the interval from 1/2 to 2. Again, we can see from the diagram or the graph here to the left that it is continuous over this, so we can use the definition of the length of an arc length. The first thing we need to do is to find f prime x and then f prime x squared. So go ahead and hit pause and see if you can solve this problem. This is a pretty straightforward integral for you to solve. So here we have the derivative of f of x. If we square that, we get 4e to the 2x minus 1/2 plus 1 over 64 e to the negative 2x. Plugging this into our definition for the length of an arc length, we get this calculation here. I'm not going to walk through the steps here. You can read through them. Hit pause now if you want to look at that. Again, I recommend that you do these problems on your own. This one's pretty straightforward. And we end up with the answer of 33/16 for the length of this arc. So let's look at example 4. What we're going to do is use our calculator to solve this integral because we currently don't have the techniques to be able to solve this analytically. But your TI-84 can solve some simple integrals for you. So let's look at the problem. Write the integral for the segment on the parabola f of x equals x squared on the interval 0, 2, and use your TI-84 calculator to evaluate. So the first thing we have to do is to find our derivative, f prime of x, which is 2x. If we square this, we'll get 4x squared, so we can easily set up the integral from 0 to 2 of 1 plus the derivative squared, which gives us the integral from 0 to 2 of the square root of 1 plus 4x squared dx. Now to enter this into your calculator, hit the alpha button and the F2 button, which is the window button at the top, and then you'll see a number of options there. Option number 4 is function integral, so select that, and then you'll see a window there where you can enter in the limits and then the formula, a square root. If you don't have a square root key, which you should have on your TI-84, you can do that as an exponent to the 1/2, which will work as well. So try that, hit enter, put your whole formula in there, including dx, letting it know what variable you're integrating with respect to, hit enter, and you should get 4.647, okay? If you're having any trouble with this, just Google solving integrals with a TI-84, and you'll find it on a simple video on YouTube.